Estimating uncertainties. This video is part of a course on food physics, of which this belongs to the modeling section. This is the fourth in a series of 5 videos on this model validation aspect with errors and uncertainties. Here we will discuss how to estimate uncertainty. And the following video, that's this one, will address estimation of error or validation. An important note is that uncertainty analysis of models is a very well-defined subtopic of research. I'm not getting into it in a formal way. This will just present somewhat of an informal way to some few simplified approaches to uncertainty computation. To repeat something said in earlier videos, models have uncertainties due to inherent variability. So let's look at this kind of a world's simplest process of canning of a conduction heated food. So in this case, this is some sort of a potato in there. Here, this is some potato cubes with meat, and it's being heated by conduction. It's a corned beef hash, if you are curious about the product. And so it's going to be put in the can, and the can is going to be put inside this canner and conduction heated. So we would like to know how long to heat. So the model is simply conduction heating. So then the material, the potatoes, they have inherent uncertainty in them because their physical properties can have natural biological variability. Now, we're doing canning, we're trying to destroy bacteria, so the microbial kinetics that we need to know, that will decide how long we're going to heat, that also has natural biological variability. These inherent uncertainties, so these are called inherent uncertainty, and these inherent uncertainties need to be considered in the simulation results that we provide. There is also this other kind of uncertainty simply due to lack of knowledge. For example, in this material here, should we include solid, liquid, gas in the transport model with kind of a multi-phase, multi-component transport model with detailed flows, etc. in this mixture? Or does the material, let's say the potato material, gets transformed so much that it changes the properties very significantly? Should we include all this and make a more comprehensive model? Now, obviously, we can build this kind of improved models, but we can never completely get rid of this uncertainty in our lack of knowledge. Quite often, we simply need to note these unknowns when we present our model simulation. So these are going to be these the possible multi-phase transport or material transformation. These are my lack of knowledge uncertainty, also called epistemic uncertainty. These are things that we often have to live with. The inherent uncertainty, on the other hand, needs to be estimated as much as possible and presented with the model simulations. And that's what this video is about. So we are trying to address this inherent uncertainty. Okay, it could be in the physical properties, or it could be in the microbial kinetics. So let's say our microbial kinetic rate constant varies over this range. And what would be an obvious way to consider this range of microbial kinetic data? We run the model with heat transfer and kinetics for each extreme parameter value. So we run it for this condition and we run it for this, and that gives us simulation results for the two extreme situations, covering all the possibilities. But this is not as realistic, since the extreme values are not as likely. It is ignoring the fact that most of the values would be close to here. So for a more realistic way to do would be to pick as many values as we can randomly from this distribution. So not just the extreme values, but pick as many values as we can from this distribution and run the model for each condition. So we will more likely choose values near the mean. So these are the two approaches. Either I consider the extreme values or just the range, or I consider the entire distribution. So I pick randomly from the distribution. Now here we want to list those two approaches that we just mentioned and a few more. We will get into more details of how exactly we do the computation in a moment. So among the simple approaches is the range that we just talked about, but that was for a single parameter. That is, we were just varying the microbial kinetic parameter. But the thermal property, for example, of the potatoes, that can also vary, and those two things happen together or can happen together. So if we consider the variation of both of these, that is more realistic. So how do we combine the effect of these two simultaneous variation? I'll show you one simple process later on, but it's not easy to consider these. Okay, so these are the simple approaches. The other list we have here are the more comprehensive and therefore more complex approaches. We already talked about using the distribution in the previous slide. We can also reformulate the governing equation. We can also reformulate the governing equation into an equation for the mean, let's say, of the temperature, and another one for standard deviation of temperature. So this kind of work also has been done quite a bit, and even in food context. We're not obviously going to get into details of all of them. So the simulating the model for these different values of parameters is also called sensitivity analysis of the model, or simply sensitivity analysis. So we're going to look into a little bit more details of this sensitivity analysis and the reasons for doing this. Now, sensitivity analysis of the model to input parameters is important for multiple reasons. It's not just for estimating the uncertainty, like due to the variability in properties or input parameters. For example, often an end goal in modeling is to obtain directionality, which way things change if a parameter changes in one way. It's directionality for design. So we try to find changing which parameters that we have control of would take us in the right direction. So that's one of the end goal in modeling. Sometimes we do sensitivity analysis as part of model building simply to see if the model is behaving right. For example, we change a parameter that we know qualitatively its effect um, of to see if it is going in the expected direction. So that's just model building. We still haven't built the model, but just trying to see if it is acting right. So those are the several reasons, one, two, three, several reasons for doing sensitivity analysis. But for now, our context is estimating the uncertainty in the model due to various parameter uncertainty, like this one here, various input parameters, including properties. So how exactly do we perform sensitivity analysis? Let's look at an example of the first one. Here is an example of sensitivity analysis to do uncertainty estimation taken from literature. Now here we're doing for one parameter at a time, and we are doing range as opposed to distribution. So here is the physical problem. This is a leaf surface here showing the stomatal openings, and there is a drop of water on the leaf surface. This is the water, and this water happens to be contaminated with bacteria. The problem, the research work studied the bacterial infiltration into the leaf. Now the bacteria enters this way by chemotaxis, where it is attracted to the sugar formed inside the stomata, and also the movement can be due to bacterial motility, which is the random movement of the bacteria. Now, there is uncertainty in the parameters that describe chemotaxis or the motility. From how do we get an idea of this amount of uncertainty or the variability? Typically, almost always we look into the literature, see all the data that have been reported. From there, we get an idea of how much these parameters vary. So based on that, we assumed here, or this study assumed plus or minus 30%. And then we ran the model, varying one parameter at a time. So let's say we varied the motility parameters, we decreased it by 30%, ran the model, then we increased the parameter by 30% and ran the model. How we interpret the results is by varying plus or minus 30% of the nominal value of the motility parameter. The final result, which in this case is the amount of bacterial infiltration into the stomata, that varies from like minus 0.25% here to plus 2.25%. So for this variability in the chemotaxis, in this case the motility parameter, the infiltration amount varies by this much. And below it shows the same thing for the chemotaxis. So this is the way to get a range of uh, variation in whatever it is that we are looking for due to variation in the parameters. And that's how we do the sensitivity analysis, and this gives an idea of how much variation to expect or which direction to go. So that was an example of varying one parameter at a time, and we considered its range, from -30% to +30%. Now we want to combine multiple parameters and the variations, but under very restricted situations, because the general problem gets very complicated. So that was when one parameter was varying, and it was varying, let's say, -30% to +30%. But now we want to talk about sensitivity analysis when we combine simultaneous variations of input parameters. So it's multiple parameters varying simultaneously. And what would be an example of this kind of multiple parameter variation? Of course, that is the norm, that's everywhere, but a simplest example could be, as let's say we're doing a heat transfer problem. So there's natural variability in thermal conductivity, density, and specific heat. How do we find out how much our simulation results will vary when all three of those parameters, the thermal conductivity, the density, or the specific heat, they vary simultaneously? Now, the answer to doing these simultaneous variations, it can get really complex. So the formula that we're about to derive is valid for a very restricted condition. And what are the restrictions? So here are some of them. So probability of, let's say, K, the thermal conductivity, to be within some range and centered around an estimated value is known, meaning we kind of nicely know the distribution and the mean and standard deviation of these values. So let's say K is the average value. This is my K, and then here is my lowest value, K minus delta K, and here is my highest value, K plus delta K. So all this stuff is known. So which means this delta K amount is known. This is my delta K amount that is known. Then the other condition has to satisfy this probability distribution, like the way you're seeing here, the normal distribution. Probability distribution is similar and normal for all parameters. Okay? Then the parameters are independent of each other. This may or may not get satisfied. These are quite restrictive conditions. Under these restrictive conditions, if we have variability in K, rho, so let me write this, K, rho, and Cp, simultaneously, the combined effect of all these variabilities will lead to a variability in T as given by this, or we can think of as uncertainty in T, delta T, given by this formula when the individual variabilities or uncertainties are given by K, rho, and Cp. Um, so what we do is simply run the model for two values of K. If we run the model for two values of K, then we get two different values of T for two different values of K. From there, I can estimate del T over del K. Now, if I choose, let me clean this out. If I choose the del K in a little bit clever way to reduce our work, so if we choose K star, the K star is one value and K0 is the other value. And if we choose K star and K0 in a way that K star minus K0 is this, meaning half of the variation that we find in K is given by K star minus K0. So this is my K star for which we run the problem, and this is my K0 for which we run the simulation, and I get a temperature for K equal to K star by just setting K to be K star and running the problem. Then I set K to be K0 and run the problem. So I get two different simulation results, T at K star and T. So if I take those two values and calculate this expression, so I got this from the model, that multiplied by my K star minus K0 is going to give me an estimate of what I need. Remember, I was trying to estimate this guy. It's but then because of the way we chose this K star and K0, these two cancel out. So I only have this left. And so then it becomes very easy now to calculate each one of these quantities. Meaning my uncertainty delta T is given by given by square root of T at K equal to K star minus T at K equal to K0 squared from here, plus the same way T at rho equal to rho star in exactly this similar way, rho equal to rho 0 square plus T at Cp equal to Cp star minus T at Cp equal to Cp0 squared. So all we have to do is run the simulation 6 times. One for just changing K to K star, one for changing K to K0, then we put the K's back into the typical value, which is K star, and then only change the densities, and likewise then I put the densities back to its normal value and run it for two different specific heats. So 6 runs and it gives me an estimate of delta T when all of these parameters K star K, rho, and Cp, they all vary simultaneously. But this estimate is contingent upon all of these restrictions that we mentioned and a few more. but it still gives you some idea of when all three parameters are varying simultaneously. So the two examples that we just finished were using range or extreme values, either a single range or combining multiple parameter variation, but still just the range. A more comprehensive one could be not just the range, but using the full distribution of how that parameter varies. Now, without going into all the details, I'm going to describe just one of these more comprehensive approaches, which is the one known as Monte Carlo, uh, that is most commonly used and it's quite easy to do. So we're going to do Monte Carlo using a distribution of parameters. Here, distribution of parameters, and we choose again this world's simplest uh, um, physics or process in food engineering, that is sterilization of solid in a container. That's our process. It's just heat conduction. The bacterial destruction inside has uncertainty due to variation in its kinetic parameters. Now we're going to consider this D and Z values to describe the first order kinetics. D is D stands for the reaction rate constant, and Z stands for its temperature dependency. These are the most common parameters used in food, so we're going to use them as is, the D and Z value. And so in this first order kinetics, these parameters have variability or uncertainty. Now in this work, we considered 10%, 20%, and 50% variation. Let me explain in a second. So these percentages are coefficients of variation. So that's standard deviation divided by the mean. That's how we are uh, describing the amount of variability or amount of uncertainty. And then how do we get this 10, 20, and 50? This is from using literature values that guided us. And then how do we know the distribution of these parameters? So in this case, if these are D and Z values, as we as they're varying, what distribution. Now this kind of data is generally not there in the literature. So when there isn't enough data, then these the authors, it's actually our work, and so we assumed uniform distribution in both D and Z. And then, so from this distribution of D or Z, we choose a set of random parameters. So we generate a set of random numbers and choose a D value and a Z value and do a simulation. Then go back and choose another D and Z values and run the simulation again. So we keep doing it for many, many times, and then the final result is plotted here. So instead of having just one value of how much sterilization took place for a certain duration of heating, now we're going to have a distribution of sterilization or log reduction that took place because of the variability in D and Z. So notice that it's not just the possible range that we got, but we got the full distribution. um, you know, it's not the lowest value of sterilization or highest value, but we got the entire distribution of sterilization. So we know which values are more likely. So it's a more comprehensive information. So this makes this process of doing Monte Carlo and choosing from a distribution, running it many times, makes it more comprehensive than just providing the minimum or maximum. But the downside, of course, there is a downside, is that it needs a lot, lot of run time for the model, something like at least 500 runs to get one of these distribution. This is because if we are choosing values of input parameters from a distribution and running it, we need to choose enough number of times. We need to choose enough values to really represent the distribution. Now, for a simple model as this one, it's just conduction heating, so the actual physics of this is quite simple. So it worked out. For more complex models, we typically run into runtime problems to do that many runs of a complex physics. So this is a good comprehensive one, but it often works only for the simpler processes. Now here is a second example. It is a more complex implementation of Monte Carlo in a more complex for a more complex physics during storage of fruits, where we have diffusion reaction process going on and quite complex reaction. What is really interesting, the reason I really wanted to share this one about this what is interesting about this example is that they considered the geometry of the fruit, the pear, as one of the uncertainties, which makes it very realistic. And so they considered their input data. They use the 3D geometry. They had a geometry generator where they varied the geometry. They considered a number of geometry, and they considered different diffusivities of the gases inside the fruit during the storage process, and they also considered different respiration rate. And if you are more than welcome to look at the details of this research, all the details are provided here. So the physics itself has uncertainties due to natural variability in diffusivity of gases inside the fruit and the reaction rates of the biochemical processes. So you can see, as I said, the details in the publication. Lastly, in these more comprehensive uncertainty propagation methods, we have ways to reformulate the GE. This is a lot more complex, and I'm definitely not getting into it, but a lot of work, a lot of pioneering work has been done by this group that is available in the literature in the food context. And one representative publication is mentioned here. You can start from here if you would like to get into more details. So I'm not going to get into any more details of this one. Before I summarize, I would like you to think of how you would apply all this. How would you perform sensitivity analysis in the context of a project that you were thinking? I am assuming, if you're doing this, if you're watching this video, you must have a project in mind. So then you want to think about what variables are you going to include the sensitivity or the variability? What variables are most important? Sometimes we don't even know which variables are important, and the sensitivity analysis itself would tell us which variables are important. And then for each variable, what parameter ranges are you going to choose? And that, of course, literature gives us guidance. Are you going to do range, the extreme values, or are you going to do a distribution? It depends on what information is available, how complicated the physics is, because if you try to do distribution, it's going to, Monte Carlo takes a lot of time. So you have to consider a number of factors. So I would like you to think about this either now, pause the video, or think about, or right about after the next two slides that summarizes. Summarizing then, one of the two sources of uncertainty in a model is the inherent uncertainty due to biological or other variability, like these: variability in physical properties or variability in biological kinetics. The other type of uncertainty that we are not going to get in details that we mention is the knowledge uncertainty. Okay, so this inherent uncertainty, there's two straightforward ways to estimate this uncertainty, and it is to run the model either for a range of values or for a distribution. So the simplest one is to run the model for the extreme values of parameters. So choose the extreme values, the red one being the easiest to do and more common one. You can also combine under restrictive situation. The other more comprehensive approach instead of range is to use a distribution and do Monte Carlo. And that is also common to be able to do. I have it in red because that's also something that quite often people end up doing. The other choice, reformulating the governing equation to get uncertainty propagation, and then combining multiple parameters, those are the fancier approaches that need more training and more resources. These methods here are more comprehensive. They provide a more complete picture of what is to be expected, what values are likely, and what range would be possible. But these are more computation compared to the simple approaches. Finally, where does all this fit in the big picture? When we take a real world process like canning, when we replace it with a model, with a mathematical model, like in this case the heat conduction equation, we have to remember that there are uncertainties in what we predict using the model. For example, this model prediction of log reduction, so we combine this temperature plus kinetics, and we predict the log reduction, but the kinetic parameters, if we use a single value and then the model gives us a single value of the final sterilization, that is not realistic, as there are biological variability in these kinetic parameters or in the physical parameters. So providing a range of values, the final results for the variability in the parameters gives a more uh, complete information. Uh, it can be range, or better yet, a distribution that will give a more complete picture. So this is what it could look like. So instead of having a single value for log reduction or a range, the best would be to provide a distribution of the final results that shows what values are more likely because of the variability or uncertainty in the parameters. Even if we give a range, that is better than giving a single value. So this is how we try to include uncertainties in the parameters or variabilities in the parameter of the uh, uh, model.